Everyone, so this is the last lecture slide dealing with heat and work. Now this is nice because a lot of it should be kind of a rehash of what we learned in earlier thermal classes. So nice way to kind of end this summer course. So we kind of mentioned this before, but we started talking about some of the processes. Um, Taking a gas or a substance from one state to another, in ways such like isothermal, isobaric, isochoric, isovolumetric, iso, iso, isentropically. Um, Now, what we're going to do is we're actually going to talk a little bit more about taking a substance from one point and undergoing through multiple processes before returning to that same initial point. And this is going to end up resulting in a very cyclical process. So we talked a little bit about heat. We talked about work. Remember, heat is specifically the transfer of energy caused by temperature differences, and work is essentially things like expanding volume in order to exert forces on the outer surfaces. And we know the relationship between them is based off of the first law of thermodynamics, which basically says that the change in internal energy within a substance is equal to the heat added to the system minus the work done by the system. A lot of this really plays into a part with typical machines, and this is kind of how machines end up working. Now, just like before, when we first started talking about a lot of the processes, uh, I had made the comment that we're assuming that those processes are reversible in order to make our lives easy. We're doing the same thing here, that when we talk about these engine cycles, all the processes are going to be reversible so that we can actually graph it and talk about it. And this is going to end up actually resulting in what we call an ideal case, where it will give us a very good approximation of the best outcome that we can get. Um, Also, when we talk about these reversible processes, it basically is referring to a fact where the entropy is going to end up remaining constant throughout the process. All right, so we had du basically representing the internal energy. Um, I had mentioned before that this tau d sigma is representing the heat added or removed from the system. So we can actually rewrite this thermodynamic identity as this. Or another way of writing it would be something like this. So we're just replacing a lot of those terms like the tau and entropy with what it's supposed to represent, heat. And same thing with the work. We're getting rid of the pressure volume aspect and just going back to the basic, it's work. Um, so basically, whenever we talk about the term work, we're specifically referring to any form of mechanical energy. Um, and yeah, that's pretty much it. Um, Nothing else from there. So, what this says here, and it is a very important aspect to kind of note about these engines, is that when we're doing work, it is technically possible to take all of our work and turn it completely into heat. But it is not the same as we won't be able to get the same result going from heat to work. Only a small portion of the heat can actually be turned into usable work. And this is due to the fact that there is a very strong relationship between work and entropy. And as you know, the entropy of a system can never go down. In these ideal cases, it can only remain constant, and in the real world, it will only increase. So here, what it says is that as the heat enters into a system, then we also end up getting entropy entering into the system, entropy increasing within there. But the amount of entropy for these cases, at least, the amount of entropy that comes in has to equal to the entropy coming out. So the heat that enters in also ends up having to leave the system. Now, the important thing is that it's not an equal amount, mainly because of the fact that there's temperature involved. So if you remember, the entropy equation is heat divided by temperature. So the there's pretty much an inverse relationship between the two. But if heat comes in at a high temperature, let's say, then the entropy has to be the same on the other end, but that basically means that at the lower temperature, we're going to have a lower heat, essentially. So this is the whole process of engines. It's using, in a very layman terms, it's taking advantage of the natural flow of heat from a high temperature source to a low temperature source in order to get some usable work. Um, or another way of saying it's uh, allowing heat to come into a system, getting as much work out of it as we can before we expel it into a lower temperature system. So again, in these ideal cases, the entropy into the system has to equal to entropy out of the system. So that means that the Q over tau for both has to be the same. And then here it kind of says what I said before about how the heat entering into the system has to be greater because the temperature as it comes in is expected to be greater. Because again, heat naturally flows from a high source to a low source. So this temperature T in is going to end up being bigger than T out. And because these ratios have to be the same, that means Q in has to be greater than Q out. Because of the fact that this inner terms are usually at the higher temperatures and these outer terms are the lower temperatures, we usually call these a hot section and the cold section, or hot temperature and low temperature. So just keep that in mind. You know, I might not use the subscripts in and out, but you might see it, H and C or H and L or something like that. Yeah, just like that. Um, one thing that I probably should also mention is that when we're talking about these engines, because remember, an engine is a combination of processes that goes from some state all around to different states before returning back to that original state. Now, the thing to note is when we say that these processes are reversible, we mean the entire process is reversible. One single process may not end up having equal entropy because, for example, an isothermal process will end up gaining heat, but the temperature is not changing. So that means if we did a difference in the entropy, uh, we'd end up having either a positive or negative depending on if we're isothermally expanding or contracting. But essentially, we just would end up having a different entropy based off of it because the temperature is the same. So the thing to note though is that if we figure out the entropy or the change in entropy for every single process during a closed cycle, then eventually when we get back to the original, we will find that the two entropies are the same. Yeah, so this is actually a thing that we need to make sure is that whenever we have a cyclical process, it's always set up so that the initial state going back to and then going back to the the final state will always end up satisfying this concept that the entropies remain the same. All right, so what we can end up having is a relationship of the heat written like this, since a lot of times we'll know what these temperatures are. Sometimes these temperatures are usually called the operating temperatures. They end up becoming very important later on. So the amount of work that we get, and this is actually a straight definition of an engine, is basically always going to end up being equal to the difference in these heats. So if we get 500 joules of heat and 300 joules leave, those remaining 200 joules had to go somewhere. And in this case, they're going in the form of work. So this is just using the definition of conservation of energy. But if we use this relationship between the high heat and the low heat into our work equation, we end up getting an equation that basically solves for or is related to the operating temperatures as well as this high heat term. We could also rewrite this so that it's in terms of the low heat. Doesn't really matter though. All right. Now we could also use this now to actually create the efficiency of an engine. So the efficiency of an engine, and this is true for pretty much any of these processes that we're going to talk about, because we're not just going to talk about engines today. We'll talk about fridges and ACs, but the whole idea of efficiency is just like how you would normally think of it. It's how much, it's a ratio between how much are we getting out, how much of the thing that we want versus how much are we putting in. You know, if we're putting in a whole lot of energy but we're not really getting a lot, well, that means that that's a low efficiency. If we're not putting in that much and we're getting in a lot, that's a high efficiency. So what we want to get from a heat engine is work. That's the whole point. We want some sort of work, and the stuff that we're putting in is that QH term. So efficiency is going to be defined in this for heat engines specifically, defined as work divided by QH, because it's what we want divided by what we put in. Um, so going back here, an engine that's 100% efficiency will be one that takes all of this input and turns it into this work, and essentially leaving no exhaust heat. That's a or QL. Remember, as I said, a lot of times QL is going to be given that term or phrase as exhaust heat. Um, so we can actually take this and we can actually rewrite it in terms of temperature. And this is actually going to give us what we call the Carnot efficiency. So the Carnot efficiency, which is still this equation, but for a reversible process, is represented by this. So this is what we can use in order to find the Carnot efficiency. Now the Carnot efficiency, there's a few things that I want to comment about it. First, as it says over here, it is used as the highest possible efficiency for a cyclical engine. And it's based off of the operating temperatures that it's working at, you know, the high temperature versus the low temperature. So essentially, what this allows us to do is we can create an engine in the real world, and then by knowing the temperatures that it's operating at, we can figure out what the maximum possible efficiency of this engine is. Typically, for most real life engines, the Carnot efficiency is going to be about 50 to 60%, while the actual efficiency is going to be like, you know, three quarters of that, being around like 30%. So this is kind of the whole point of the Carnot efficiency, is that it gives us a nice estimate or approximation of that highest possible efficiency. Now, there is a little bit of a caveat. The second thing that I wanted to mention is that technically the Carnot efficiency really only works for a very specific type of engine. Um, I don't think I have it up here, but this is a isothermal adiabatic engine. So an engine, I think this is typically related more towards steam engines, but it's a process that takes you from some initial state, undergoes an isothermal and adiabatic process of expansions, then an isothermal and an adiabatic process of uh, compressions, bringing you back to that original state. If we wanted something closer to um, like a car engine, then what you would normally do is you would use a slightly different cycle and a different equation called the Otto cycle, which is um, trying to remember, it's an adiabatic isochoric uh, double process, reversible process at least. And the efficiency that comes from the Otto cycle is a little bit different from this. So I just wanted to point that out, that there are actually other efficiencies out there based off of different uh, engine cycles. So, like if you end up having a cycle that undergoes other types of processes, like maybe it's an isobaric, isochoric, that would technically have a different efficiency than something like this, a different like max temperature efficiency. However, this is pretty much good enough for us to be able to answer a majority of the questions. So we're just going to use this as a nice little catch-all for peak efficiency. But I just wanted to mention that really quickly, that technically this Carnot cycle is a specific type of cycle. All right. So I said before that every single real engine is going to end up having some efficiency less than this Carnot efficiency. And that's mainly due to the fact that technically these entropies aren't the same. Uh, During a real process, a real irreversible engine, um, there is going to be some additional entropy created through getting the work. And this is going to end up giving us a output entropy greater than the input entropy. This is usually caused by the natural friction that exists between all the things. And anytime we get some sort of um, an energy change, there's always going to be some added form of entropy. So we can actually go back to the equations and just get a representation between the irreversible and the reversible process to kind of show that this is true. So what we can do is saying that for any engine, real or imaginary, reversible or irreversible, we end up having this situation that the exhaust entropy is going to always be greater than or equal to the input. That means that this is going to always be true, or that the exhaust heat is always going to be greater than or equal to the input heat times the temperature ratios. Doing the same thing by taking the equation that we had for work, plugging this in, we end up getting this being less than the Carnot efficiency and this. So bringing this over, we end up getting that the actual efficiency is always going to be less than or equal to the Carnot efficiency. So again, this statement that the Carnot efficiency is going to be our ceiling of efficiencies. Now, I did want to say one last thing. This is a generic efficiency equation. It is something that is always true no matter what. It doesn't matter whether we're talking about a real system or an imaginary system, a reversible or irreversible, whether we're talking about, you know, a Carnot engine, a Otto engine, or any sort of type of engine, this efficiency is always true. This equation is the general form. This equation is a very specific case specifically for Carnot efficiency. So you want to make sure that you kind of um, keep an eye out for it. Don't just immediately plug numbers in here if they're asking for efficiency. You want to kind of note whether it's specifically asking for the Carnot efficiency or the maximum possible efficiency or something like that. But this statement basically saying that the actual efficiency is always less than the Carnot efficiency is what we can call the Carnot inequality. And it's showing these three statements. The first is that real engines can never be more efficient than their ideal case. And note that I'm saying their ideal counterpart. Again, there are different types of processes and different types of engines. If you compare a combustion engine with a steam engine, well, with the reversible ideal steam engine, that's not really going to work well because those are different types of engines. So you need to make sure that you kind of relating it back to its ideal counterpart. The other is that this temperature ratio is really what depend or dictates how efficient an engine is going to be. And as this ratio gets closer to zero, then your efficiency gets closer to 100%. Or another way of saying it, this exhaust temperature has to get towards zero. So the closer this is to absolute zero, the closer this becomes to a perfect efficiency engine. So this also kind of means that the only way we can possibly get a 100% efficient engine is if our exhaust temperature goes to absolute zero, which, as far as I know, is not really a possible thing. All right, so this is what I said before, that TH and TL are usually the operating temperatures. Typically, for most engines, TH is the temperature of what's going on inside of the engine, while TL tends to be the environmental temperature around it. So going back to what I said before about how the only way we would get 100% efficiency is if our exhaust temperature was at absolute zero. That means we would have to have the engine running within an environment that's at absolute zero. Now, you might think, is it possible to take this engine, send the exhaust to a container that's at absolute zero? And you'll see why in a bit that is not possible. But yeah, so a lot of times in the real engines, as they say here, that ambient temperature is going to be around 300 Kelvin because that's the typical environmental temperature around us. Now, what that usually means is that in order for us to get very high efficiencies with this natural 300 Kelvin ambient temperature, then the only other way to actually get that efficiency higher, because remember, we have to get the ratio as low as possible, is to make TH even higher than this ambient temperature. But the problem there is that the substance that we work with, they limit how high the temperature can be. For example, we could technically make an engine where the highest temperature is as hot as the sun, but none of our physical materials will actually be able to sustain it. So you need to make sure that you end up getting a balance of this, getting the temperature as high as possible to work with the materials that you're working with, and then having that ambient temperature of 300 as a limiting factor. So here's just a typical example. For a lot of steam turbines, the high temperature is going to be typically around 600 Kelvin. So that means the Carnot efficiency is going to be about 50%, what I had mentioned before. But of course, if we actually look at the actual efficiencies of these, it would probably be closer to like 30%. Now, this is a typical internal combustion. I forgot the exact name. I think it's a four-stroke combustion cycle. Basically, this is what ends up happening. So, a gas air mixture basically comes into this container, pushes this piston down. So, as the piston goes down, it undergoes a momentum. It carries its momentum through, but then it ends up lifting up again due to the momentum. This gas ends up becoming compressed until the piston actually strikes a little spark plug over here, which ends up creating a little spark, igniting all the gas within that gas air mixture. What that ends up doing is it actually causes the piston and the gas inside this area to expand a second time, pushing the piston down, and then as it comes up, it ends up exhausting, pushing out all that exhausted gas mixture. So that ends up being the typical combustion cycle. All right, so these are some examples of why an engine would end up becoming irreversible. So first off, this ends up being a big issue is that, as you know, heat can be trans transformed or translated or transferred through materials. Materials, as much as we would love them to not be to be isolated scenarios, technically aren't. So some of this Q heat can actually flow straight to the low temperature environment through the walls of the container. So that means that our input heat would technically be a lot less than what we would initially assume. Another one would be things like the temperature difference may not be as accurate as we think. Um, then we also have things like this that part of that work ends up being lost through to friction and heat and other things like that. Here, this would end up being a big issue that gas might end up actually having a free expansion without doing any work. So that's something that we would end up becoming an issue. But the whole idea is that there's things going on that we can't really account for, and as of now, can't really limit as best we can. So with that being said, we'll do a few practice questions dealing with these heat engines. So pause video, work on itself, and we'll go over it in a second. All right. So for part A, they want to know what is the highest electrical output based off of these temperatures. So what that means is they're telling us that the amount of heat being dumped into the river is limited by this. This is our exhaust heat. That's what that's referring to. So because we're talking about a reversible process, the ratio of the heat divided by temperatures have to be the same for the high end and the low end. So if I'm trying to figure out, well, how much input heat did we have, I can use this by plugging my numbers in, making sure that these temperatures are in their Kelvin state to get that the input heat is this. Now, one thing that I want to mention is that this is in watts, but it doesn't really matter. So the work, as we know, is the difference between our input and our output heat. So I take the difference between those two numbers, and I end up getting this. That the amount of work that we can get, the maximum amount of work, would be a little bit under 2,500 megawatts. Now, it asks here, how would this change if we are able to raise the steam to, um, or if we raise the steam to by an extra 100 degrees? So we just redo all that calculation. So we redo our input heat calculation, we end up getting that it's a little bit higher, and we find that the final temperature ends up being, I think I have to fix this number because I think this 6 isn't supposed to be there. But we end up having essentially a little bit under 3,000 megawatts. So it ends up increasing by only 500 ish megawatts. So it's not a huge increase in our energy output, despite the fact that the temperature increase would actually be probably much higher than we could sustain. All right, here's another question. Pause the video, work on itself, and we'll go over in a second. All right, so here, first they do tell us that the plant is operating at this Carnot limit. So we're going to want to find the total work based off of this setup. So it says the initial temperature is at the high end, and by the time it ends up going to the final temperature, it's still there. So um, they say here that the temperature of the rock is going to be dependent on this, the MC delta T essentially equation, where C is the specific heat. So if I take the equation that I have for that relates work, heat, and the temperatures, I end up getting this. Um, Plugging in what they give me for the heat, I get that. Then what I can do is I can actually just integrate this, because whenever you see this like a dq and dt, means that you're probably going to have to integrate at some point. So you integrate between the initial and final temperatures, plug it in, and we end up getting this as our final answer. All right. Here's a continuation of that. So pause video, work on the stuff, and we'll go over in a second. All right. So from here, I just take the equation that I just found, plug in all these numbers that they're giving me. I get that the work ends up being 2.49 times 10 to the 19 joules. Now, if you look here, they want this in kilowatt hours, which is a very common unit of energy. So we're going to have to play around with the unit here in order to get to kilowatt hours. The way we do that is by dividing the whole thing by 60 times 60 in order to go from, because remember, joules is technically watts times seconds. So we had to divide it by 3600 to bring it to hours, and then this to give it to kilowatts, and we end up getting kilo, and we end up getting this number of kilowatt hours. All right, I'm going to pause the video there, and we'll continue our discussion when we take the reverse of these heat engines in order to create fridges. All right, if you have any questions, let me know. Otherwise, I'll see you later.